Here's another separable differential equation. In this case, we have an initial value problem because we're told that initially when x is 4, y is 1. It kind of gives us a starting point for figuring out what y is. So we call this kind of differential equation an initial value problem. And this one's separable because you can break up the root of the product as the product of the roots. So this is really the square root of 2 times the square root of x, which for convenience I'll just write as x to the 1/2 times the square root of y, which is y to the 1/2. dy dx equals 1. I can move this x over here, and I'll have the square root of 2 times y to the 1/2 dy dx is equal to, let's see, if I divide by x to the 1/2, that's really x to the negative 1/2 over here. Now that I've separated those, I can see if I integrate with respect to x, the integral on the left becomes the antiderivative of root 2 y to the 1/2 and dy dx times dx is dy. Okay, we did separate out. This is just an integral with respect to y. It's easy to do. Y to the 1/2 becomes y to the 3/2, but we are going to need a 2/3 there. X to the, oh, this was x to the negative 1/2. That becomes 2x to the positive 1/2. And both of these have an arbitrary constant. I'll just move them over here. The difference between two arbitrary constants has to be yet another arbitrary constant. Now our next step would probably be to solve for y. However, because we have information about the value of y when x is 4, this is telling us when x is 4, y is 1, right? We're thinking y is a function of x, so there's the name of the function. This stands for its input. The input values are x's, so this is saying the input is 4 and then the output is 1. We can figure out what the constant c needs to be. Now's a good time to do it because right now we have the constant all by itself. So let me plug in 4 for x. If I do that, this is the square root of x. So the square root of 4 is 2, and 2 times 2 is 4, plus c on this side. Over here, if y is 1, if you cube 1, you have 1 still, and the square root of 1 is 1. So right over here, we just have 2 root 2 over 3 times 1. And that allows us to solve for c. c is 2 root 2 over 3 minus 4, or if you like common denominators, that's we need a denominator of 3, huh? Negative 4 is 12 over 3, so 2 root 2 minus 12 all over 3. Now we can go back and, oops, we have 2 root 2, not root x, 2 root 2 over 3 times y to the 3/2 equals 2x to the 1/2 plus c, which we just figured out was 2 root 2 minus 12 over 3. Now I'm just going to solve for y. So we've got the differential equation integrated. We have a relationship between x and y instead of a relationship between x and y and the derivative of y. We had information about how y was changing, and now we have enough to solve for y. First thing I want to do is probably get rid of this 3 by multiplying through by 3. I get 2 root 2 y to the 3/2. 2 times 3 would be 6x to the 1/2. And you multiply that by 3, you'll get your 2 root 2 minus 12. Next thing I could do would be to divide by 2. So we get root 2 y to the 3/2 equals 6 divided by 2 is 3x to the 1/2. 2 root 2 divided by 2 would be root 2, and negative 12 divided by 2 would be negative 6. Let me now divide by square root of 2. Y to the 3/2 equals 3 over root 2 x to the 1/2. Root 2 over root 2 would be plus 1 minus 6 over root 2. We could rationalize the denominator, but to get y alone, all we need to do is to raise things to the 2/3 power, because the power of a power is the product of the powers, so we get 2/3 times 3/2 is 1, so y is alone now. 3 over root 2 times x to the 1/2 plus 1 minus 6 over root 2 to the 2/3 power. We have now y as a function of x, right? And we've recovered that, and it not only will this, if you check it, this will satisfy this pattern in the derivatives. If you take dy dx and multiply it by the square root of 2xy, you'll get 1, but also if you plug in 4 for x, you'll get out 1 for y. Let's do another separable problem. This one we can separate because we can rewrite these powers. E to the x plus y is the same thing as e to the x times e to the y, because if two numbers have the same base and you multiply them, you can add the exponents. Same thing down below, we have e to the 2x times e to the minus y. Next thing we can do is say, well, this is a little bit simpler. E to the x divided by e to the 2x would be e to the x minus 2x, since those two numbers have the same base and you're dividing them, and x minus 2x is negative x. E to the y minus minus y would be e to the 2y. Now we can see this is a function of x times a function of y, so we can separate dy dx over e to the 2y equals e to the negative x. So that if we integrate both sides with respect to x, dy dx times dx becomes dy over e to the 2y. Let me write that as e to the negative 2y. It'll be easier for me to get the antiderivative. And on this side we have the antiderivative e to the negative x dx. Well, the antiderivative of e to the negative 2y would be something like e to the negative 2y, but when I take this derivative, there's going to be e to the negative 2y times negative 2, so I'll put a little negative 1/2 out here. I'll do something similar here. This is going to be e to the negative x, but I need an extra negative so that when I take the derivative it becomes positive e to the negative x. Both have an arbitrary constant, so let me throw that in. Next thing would be to multiply through by negative 2. I get e to the minus 2y equals, if you take negative 2 times negative e to the minus x, you get 2 e to the minus x. Negative 2 times an arbitrary constant is another arbitrary constant, so I'll go ahead and just call that an arbitrary constant. Since this is an initial value problem, this is saying that when x is ln2, y is 0, now would be a good time to solve for my constant c. If y is 0, on this side I have e to the 0, which is 1. If x is ln2, I have 2e to the negative ln2 plus c. Or, let's see, since ln2, I can bring that negative up using a power rule for logs. So I really have the natural log of 2 to the negative 1. E to the natural log of 2 to the negative 1 would just be 2 to the negative 1, 2 to the negative 1, which is 1/2. Okay, so this is 1/2. So 1 equals 2 times 1/2 plus c. 2 times 1/2 is 1. So I know in this particular case that c is 0. So I have because of my initial condition, I found my constant, and I figured out that that constant is 0. Now I'm ready to continue solving for y. I'll take the natural log of both sides to get negative 2y equals the natural log of 2 times e to the negative x. And I can use the product rule here. Negative 2y equals the natural log of 2 plus the natural log of e to the negative x, which gives me negative 2y equals the natural log of 2. The natural log of e to the negative x, that's the exponent you put on e to get e to the negative x. That must be, what do I have here? 2y equals the natural, 2 doesn't look very good. Okay, minus x. So dividing by negative 2 gives y equals negative 1/2 the natural log of 2, and dividing negative x by negative 2 gives me plus x over 2. So I've found my function now by using separation of variables.